we are live and
Yeah, please, please.
recording is also started. Yeah.
So, Professor Dr. Partha Goswami is with us. Sir is with us. Hello, sir. Am I audible? Sir, am I audible?
Yeah. But I'm present. I'm present.
Welcome, sir. Welcome,
Thank
sir,
you, ma'am.
once again to our series of lectures. And I'm glad that you will be able to tell us about the numerical and the analytical techniques of quantum mechanics problems today, which you initiated yesterday. Dr. Yogesh, I request you to kindly display the introduction slide.
And I have already displayed. Is it visible to you?
What happened?
And it is already displayed. Can
No,
you see the slide? First
the next one. Yeah, the next one.
Okay.
Introduction to the speaker.
Yeah.
The next one, please.
Yes.
Yeah. Okay. Thank you so much. So it's a pleasure for me to reintroduce Dr. Partha Goswami, who's an associate professor at the Department of Physics, Deshbandhu College, University of Delhi. He did his graduation and is with first position from St. Xavier's College, Ranchi. And he has been teaching mathematical physics to BSc Physics honors students for the past 30 years. His area of specialization is condensed matter physics theory, and he has 32 research papers to his credit, mostly under sole authorship published in prestigious journals of physics. And we all know him as a person who patiently and slowly tries to grasp the concept from the perspective of the students also. And that is the mark of a true teacher. And with those words, I welcome you, sir. We are grateful that you agreed for this lecture also and give a solution of quantum mechanics problems, which is essential to the understanding of a student. So I request you to now share. Dr. Yogesh, please stop sharing.
Thank you, ma'am. Thank you for your kind words. Shall I now make a start?
Yes, sir. Yes, sir. Please do.
Okay. So today our task is to explain how do we go about solving time-independent Schrodinger equation with complex.
Yogesh, will you share the slide, please? Yeah.
With complex potentials. Not very complex. I would start with, for example, the Coulomb potential, which is in the syllabus very much. And then I will go over to screened Coulomb potential. Of course, there we could have tackled far more complex problems. But right now, for this lecture, we shall confine ourselves to two potentials, Coulomb potential and screened Coulomb potential.
Sir, it is visible to you?
Yes.
Yeah.
Yes, numerical solution of TISC.
Yeah, numerical solution of time-independent Schrodinger equation for the Coulomb potential and screened Coulomb potential. That I'm adding from my side. In 1 hour's time, these two can only be covered. So now, exact solution of Schrodinger equation is a physical problem, is very, very crucial. As it gives a deep understanding of the physics problem. There are several methods for solving this equation, which provide us valuable solution to the problem of physical models. And for example, the potential plays central role. We have, as I said, we shall be tackling today Coulomb potential and screened Coulomb potential. Apart from that, we have Rosen-Morse potential, the Morse potential, etc., etc. For some potentials, no analytical solution to the Schrodinger equation is possible. So in this case, we have various advanced methods based on theory of perturbation, such as WKB approximation and numerical methods such as factorization, Nikiforov, Uvarov methods, etc. In numerical, for finding numerical solution of the Schrodinger equation, we have to first write down the, for example, I am working on the Coulomb's potential. So I would write down the radial part of the Schrodinger equation because that is the simplest one, and thumb rule is one should go step by step. So in d dimensions, a radial part could be, I have not written it here, I'm sorry. In d dimension, radial part could be written as d2 dr square plus d minus 1 divided by r and ddr plus 2mh square whole multiplied by energy E plus potential V and minus L in whole multiplied by L plus D minus 2 upon R square, and whole of this multiplied by R, capital R, as a function of R. I think for one dimension, I have shown this equation yesterday. So this is a generalization to D dimension. And when I attempt to solve this by numerical method, I am led to an eigensystem. Necessary boundary condition for transforming the Schrodinger equation to eigensystems must be imposed at initial endpoints, at initial time, at endpoints. Well, time of course isn't there because we are considering time independent. So at initial point, wave function must be 0 at these two initial points, and then we shall treat the problem in usual manner as an eigenvalue eigenvector problem, and there are other methods. For example, power method, reduction method, Givens method, Jacobi method, etc. So we are focusing today only on central difference method. So in central difference method, as shown in the first slide, I have written it down. This was from the previous yesterday's last slide. We had the equation 10.20, which was d2y dr square, potential VL, L is a quantum number, and yr minus 2 mu effective mass E upon k h cross square yr, where VL, the potential, is 2 mu E square R h square minus L plus 1 upon R square. One can check very easily that from the expression that I have verbally given to student for D dimension, one can easily get this one-dimensional problem. This is in the radial direction. So now we put minus 2 mu E upon k h cross square equal epsilon, capital epsilon, and I introduce a quantity called first Bohr radius, which is, I'm sorry, it should be h cross square upon k times mu E square. K is missing out here. K is 1 upon 4 pi epsilon naught. One can see easily by dimensional analysis that h cross square upon k mu E square, where mu is mass, will give me a quantity with dimension of length, which is our first Bohr radius. I introduce this Bohr radius to make the entire problem dimensionless, because then numerical handling of the problem will be too easy. you will see why it should be easy, because if you keep the dimension open, every time you write a step, you will have to satisfy yourself that you have not made any mistake and dimensional homogeneity is valid and all that and all that. So when you make everything dimensionless, you don't need to worry about this particular issue. So we have our d2y dr square plus VLR YR equal uh, capital epsilon times y as a function of r, where VLR I have expressed in terms of Bohr radius, and it finally, as one can see in the last line, it comes out to be up 1 by a0 square 2 upon r by a0 minus l plus 1 whole divided by r upon a0 whole square. So you see the term within the parenthesis is a number. R upon a0, of course, is a number. You are expressing radius in terms of first Bohr radius, so it becomes a number. And the second term also is just a square of r upon a0 square. So this is also number. And of course, the term 1 by a0 square is just the multiplier. Now with this we go to, after converting in dimensionless term the crucial part of the potential, we go to equation itself. Please go to the third slide. Please go to the third slide. So in the third slide, you can see I had made a capital epsilon also dimensionless, introducing expression for Bohr radius. Now the k term appears out here. So we have uh, 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 2 epsilon a naught k e square a naught square. That is what it is. So well, we therefore write the equation as Schrodinger equation, TISE, as d2y dr square plus the potential term, which is 1 by a0 square, and term within the parenthesis yr, and we have minus 2e k e square a0 square and yr. I believe there is no problem up to this step, and subsequent step also is uh, pretty simple. We had in fact taken a0 square 1 upon a0 square common and cancelled it out from both the sides. So that is how the third step, or the subsequent equation appears in the form as it is shown. Now we suppose r upon a0 equals some variable s, or r is a0s. So with that, our equation appears as d2y as a function of x, s ds square 2 by s minus l plus 1 s square y as a function of s, and minus 2e k e square upon e0 y as a function of s. And we are now in a position to identify dimensionless potential 2 by s minus L into L plus 1 by S square. Now the problem has, you can see the left hand side is, what is the dimension of left hand side? May I ask my students, whoever listening, what is the dimension of the left hand side of this encircled equation? Hello? Hello?
Yes, sir.
what is the dimension of the left hand side of the encircled equation?
Student, please respond in the chat box. Students are not responding, sir.
They are not responding.
Yeah, somebody has written dimensionless.
Ah, fine. That she is right. S is dimensionless. S square also dimensionless. And in the right hand side, incidentally, you have energy E, and divided by K E square upon E0, which is also energy, potential energy of electron in the first Morse radius. So energy cancel out. Perfect situation, a dimensionless specimen of an equation. So this is the equation we need to solve. We go to the fourth slide, please. Okay, so we now initiate finite difference method to solve this equation. Equation is what is written out there. VLS is 2 upon S minus L into L plus 1 upon S square, and you have in the right hand side the energy term, and Ys as usual. Suppose I use the 3-point formula to write down the second derivative. How do I go about it? I have in fact split y, let's say, into n plus 1 parts. N plus 2 parts, sorry, n plus 2 parts, and I assign j the index values 1, 2, 3 up to n, and y at 0 would be 0, and y at n plus 1, which is n plus 2th part, or the quantity y at n plus 2th part, is also 0. Why so? Reason is these y's are function of s. What is s? R upon A0. Now, the equation is radial equation. We start from value of R upon A0 to be quite close to 0, which means we are very close to nucleus, and end up at S, say, quite far off, n times R upon, or n plus 1 times R upon A0. So at electron has virtually 0 probability of being found in the nucleus. It also, because ours is one electron system, it has been emphasized in the last class, it is hydrogen atom that we are considering. So electron is neither quite close to the nucleus, which means y0 should be 0, because y is a substitute of psi or r, which is your probability amplitude. So probability amplitude of finding electron close to nucleus would be 0. Also, probability amplitude of finding electron very far away from the nucleus, n I may take very large, so very far away from nucleus is 0. That's why at the two endpoints I shall put y as 0. In between, the index j actually runs from 1, 2, 3 to n. So please remember, I have put the first term or at the beginning y0 as 0 and yn plus 1 also as 0. Reason, physical reason, electron cannot be either too close to nucleus or it cannot be too far away from the nucleus. And then the second derivative, and I take the small width of S, small chunk of the width of S, or small width of S as H. That means N plus 1 H is our total distance under scanner. H, I am taking regular interval and all intervals are equal to H. So double derivative could be written very easily as yj plus 1 minus 2yj plus yj minus 1 divided by h square plus terms of order h square. This is our 3-point formula. And in, of course, a more sophisticated formula, 5-point formula, double derivative will be minus y j plus 2 and all that, whatever is written, 12h square and terms of higher order. So I put this double derivative into in the form of a what? Recurrence. It is a recursion expression kind of thing. So I put this double derivative in the Schrodinger equation, and one can see that we have the double derivative and the potential term multiplied by y at j or y at sj. Y at j plus 1 is y at sj plus 1. So y at sj, and the energy term is minus 2e upon ke square a naught y at sj. And I had very clearly indicated yj here means actually y at sj. I believe the use of this 3-point formula for replacing double derivative as a recursion type or subsequently our differential equation, which is our Schrodinger equation, through this double derivative expression, what I am doing is the differential equation has been transformed into a difference equation. And you see, the difference equation is an equation, by definition, is such an equation where all subsequent terms are determined by the preceding terms. I am sure such kind of recursion relation or involving indices of y or solution our students had encountered in solving, for example, differential equation, second order differential equation with non-constant coefficient by series solution or by extended power series solution, they must have encountered. So I'm sure the new appearance of the Schrodinger equation is not very alien to the mind of our students. So with this, we go to the 5th slide, and I have here clearly shown how the division thing has been made. I have a line, I had taken small number, of course. I have divided this line into 5 parts, and as you can see, I had introduced the coordinates, endpoints of each as S0, S1, S2, S3, S4, S5, and I have taken Y S0 as very small. Y is 0.001. I have not taken it as y at 0. Why? Why I have not taken it as y as 0? Sorry, s as 0. Can anyone tell me? Can anyone tell me? Why have I not taken y s0 as y0 equals 0? Why an arbitrary number, small though, 0.001?
Please respond in the chat box. Sakshi Gupta has written boundary condition.
Boundary condition.
Yeah.
No, not really. Not really. Boundary condition, this itself is ensuring y is 0 and y at point 0.001 equals 0 and y is 5 equal 5 is also 0, and our width I have taken as h, which is 1, and the width will be, each width will be of length 1 Bohr radius. But why 0.001? Reason is, if I take it as 0, computer will not accept it. Reason is, our potential has 1 by s term. Go back to the potential, please. For example, one can go back to the fourth slide. Fourth slide. Go back to the potential term, which is right at the top. It is 2 by s minus L upon L into L plus 1 upon s square. So if I put s as 0, I shall encounter or computer will encounter divergence. And divergence neither analytically nor computer can deal with. So artificially, to avoid this situation, I have taken a value of s quite close to 0 but not exactly 0, so that computer does not uh, uh, reject this kind of a situation. I believe my explanation is clear to you, everybody. I said if I take s as 0, potential term will diverge. Computer will not accept any divergent term, and therefore I need to checkmate that. I need to have a term close to 0 but not exactly 0, so that computer will not be able to reject it right away. So I have here these endpoints. So how many partition I have made, or how many grid term is used actually in 2 dimension. I am reluctant to use term grid, but anyway it is 1 dimension, so let me use grid. So I have 5 grids, at two extreme points of the 5 grids. S value is 0.001 and 5, which means R value is 5 times first Bohr radius, and I am assuming neither electron is very close to nucleus, which is what y s0 equal y 0.001 equal 0 symbolizes. And I also assume that electron is not too far away, 5 times first Bohr radius from the nucleus, which is symbolized by term y s5 equal 5 equal 0. So this is set. I think this formation of grid and how did I do it, keeping physics intact, is clear to our students? I believe it is clear. Hello?
Yes, sir. Yes, sir. It is clear.
Okay, very good. Now it is my turn to put different values of j. J, I said will run from 1 to 4 in this case. Like elsewhere, like in the discussion of fourth slide, I had taken n plus 1 points, n grids, and I said that j there will start from 1, will end at n. So put j equal 1 in our difference equation, which is appearing in the previous slide. Difference equation, so go to the previous slide. Here you put j equal 1 and h of course is 1 because you have taken each grid of width equal 1 Bohr radius. So coming back to fifth slide, for j equal 1, you have equation ys2 minus 2ys1 plus ys0, which of course will be 0. You have assumed it. Then vls1 ys1 minus 2e ke square ys1. And mind you, electron is bound to the nucleus, so energy of a bound state is always negative. Therefore, I had put E less than 0 and I'm going to introduce a term, small epsilon, which is 2 times absolute value of energy divided by K E square upon A0, which of course will be positive. Now we go to the sixth slide. Here, so our j equal 1 gave me this equation, equation 1. J equal 2, you put, you get equation 2. I need not explain now. I had collected all similar terms. So we have something like y1 into ys1 minus 2 vls2. Oh, ys2 is missing. I'm sorry, please insert ys2. While writing, you do commit some mistake. ys2 is missing. 1 times ys3, then 0 times ys4, and epsilon times ys2. Third equation is obtained putting j equal 3, and I have similarly 0 ys1, 1 times ys2, minus 2 plus vls3 ys3, 1 times ys4 equal epsilon ys3, and fourth equation is obtained putting j equal 4, and it is a similar equation. So we have all 4 equations lined up. Now, what are the unknowns here? In this system of simultaneous equation, unknowns are ys1, ys2, ys3, and ys4. Correct? And coefficients are there. So I would treat this problem as an eigenvalue eigenvector problem, and I would write it in the form of a matrix. It is convenient to write in the form of a matrix. So you have minus 2 VL plus 1, 1, 0, 0, 1, minus 2 VLS2, 1, 0, and so on, 0, 0, 1, minus 2 VLS4, and these column vectors are containing the unknowns equal epsilon times the column vector, where VLS1 will be 2 L plus 1, because your VLS is 2 upon S minus L plus 1 S square. So VLS1 will be 2 times LL plus 1. VLS2 will be 1 minus L by 4, and so on and so forth. So I have this matrix as our Hamiltonian matrix. You have the kinetic energy term here, which had come from double derivative, and you have the potential energy term. And the column vectors are the eigenvectors to be obtained for eigenvalue values epsilon. So formulation of problem is clear. I think formulation of the problem is clear. And eigenvalue equation will be determinant of Hamiltonian matrix minus epsilon identity matrix, which will give me this determinant equals 0. I think eigenvalue equation is clear to everybody. Is it clear? Hello?
Please respond.
Seven. No, you are showing 7th. You have not shown 7th. 7th. Oh my God. 6th you kept showing. In 6th you had those 4 equations, and in 7th slide I have written it down in terms of matrices, and these unknowns constitute the column vector, and epsilon will be the eigenvalue. This matrix which I have shown is going to be is of course our Hamiltonian matrix, and VLS1, VLS2, etc. from general expression has been written down. Now to calculate eigenvalue, which is epsilon, I would set up the eigenvalue equation, which is determinant of Hamiltonian matrix minus epsilon times 4 cross 4 identity matrix. So this determinant equals 0 is actually determinant of the Hamiltonian matrix minus epsilon times 4 cross 4 identity matrix, that equated with 0. So I'm sure everybody is familiar with how to find eigenvalues. So this is your eigenvalue equation. I think I am clear to everybody. Hello? Hello?
Kindly
Yes,
respond
sir.
in the chat
Yes, sir.
box. Yeah.
Okay, very good.
Yes.
Now I am interested in actually the ground state for the moment. So for ground state, L will be 0. L is the orbital quantum number, and L equals 0 corresponds to the sth subshell of the hydrogen atom. So I can put L equals 0 for simplicity. So our eigenvalue equation reduces to what I have shown in the 8th slide. Please go to the 8th slide. Okay, so I have put here L equals 0, and I have obtained the eigenvalue equation as the determinant, which is shown, equals 0. How many eigenvalues I will get? I will get 4. Is that correct? Is that correct? Hello? Is that correct?
Please respond.
What's your question, sir?
Yeah.
Please repeat the question once.
How many eigenvalues we shall get? Sakshi Gupta writes 4. I think she understood it. Because this determinant is going to give me a quartic in epsilon. Is everybody following? Look at the last line of this slide. You are getting a quartic in epsilon, ultimately, after expanding this determinant. Am I clear to everybody?
I hope so, sir. It's a quadratic, so obviously they'll have.
No, quartic. I said quartic. Quartic. Fourth degree equation.
Yes,
Yeah.
sir. I understood that. Yes.
It is quartic. Students have been following. So this is quartic. And there would be 4 eigenvalues. Naturally, a quartic has 4 solutions. Now, our epsilon, if you remember from 5th slide, epsilon 5th slide, please go back to 5th slide. Epsilon is greater than 0. So, coming back to this slide 8, when I solve this quartic, I would only retain or only admissible value of epsilon will be the one with which is positive. Negative values will be inadmissible. Is my point clear to everybody? Is my point clear to everybody?
Those who understand, please write in the chat box. Yes, sir. They are writing. Things are clear.
Okay. So go to the next slide, 9th. I have solved this quartic. I have not actually solved it. In fact, quartic has, up to quartic, you have general solution. Like quadratic has general solution. Cubic, if students do not know, cubic also has general solution. It is called Cardano's solution. And even quartic has a general solution, very Lebrandine one. It is called Ferrari's solution. They were Italian mathematicians. They had solved in 16th century or 17th century probably the cubic and quartic. And since then, if you think that quintic also, quintic meaning 5th power, or hectic or heptic also will have general solution, that is not true. There is one theorem again given by a very famous mathematician called Abel. Abel's theorem says that no general solution is possible beyond quartic. So in hindsight, students should realize that why have I taken for an analytical solution? If they go back to the 5th slide, if you go back to the 5th slide, a student should now appreciate that in hindsight, in retrospect, that why have I taken 5 grids? Because I knew that beyond quartic, I will not get any solution. I will have to depend on some numerical method or the other. So therefore, I had chosen to divide the distance into 5 grids, and which led me to a system of 4 equations, and which ultimately led me to a quartic. So we come back to our 9th slide, and in fact, if you Google out, just write solution of a quartic or quartic calculator, and some page will come where you insert these coefficients and you will get 4 solutions. So that's how I have obtained these 4 solutions, and I am finding only one solution to be retained, admissible. Rest of them I have crossed them out, they are negative. So only one eigenvalue I am getting, which of course is expected because I am for the ground state or ground state energy. So only one energy I am expecting. At that energy, I find to be 14.4 electron volt after substituting the value of k e square upon a naught, etc. Now, of course, this is absolute value of energy. So actual value of energy will be minus 14.4 electron volt as per my calculation. Now my students must be knowing that actual value of this energy is how much? How many electron volt? Ground state energy of hydrogen atom. Yeah. So, Smriti Moy, Chakraborty, Priya Agrawal, they are all right. Minus 13.6 electron volt. So I am getting minus 14.4, doing a very rough calculation, taking only 5 grids. So I must pat my back that I have got some sensible result. I think my students are appreciating this point. I have taken only 5 grids. In principle, to get accurate value, I should have taken 1,000 grids. But 1,000 will give me an eigenvalue equation running in with epsilon power as 1,000, for which I have no solution. We have no solution. And humanity will never have this solution because Abel has said so. And Abel is to be believed. He was a very brainy, famous mathematician. Now, I have some, of course, I cannot stop. I can go to the 10th slide. I have taken here, I resorted to computer. For L equals 0, I have written down what is VLS. And I have written down, in fact, I have a 10 cross 10 matrix, which means how many grids I have taken. How many grids? How many grids I have taken? If Hamiltonian matrix is coming out to be a 10 cross 10 matrix, how many grids I have taken?
11.
Correct, very right. Sriti Moy Chakraborty. Good, very good. 11, very good. Okay. So I've improved upon myself, taken 10 grids within the same distance. Acha, now computer, I have done it, I solved it by Matlab. You can equally well do it by Scilab. Matlab, of course, is not available free, whereas Scilab is freely available. Anyway, so mine is the Matlab will not accept within bracket anything other than integer. So I had V01, V02, 1 symbolizes Bohr radius, R equal Bohr radius A0. And V02 symbolizes R equal 2 times Bohr radius, and so on. V10 symbolizes, V010 symbolizes 10 times Bohr radius. And endpoints are the S equal 0 and S equal 11, out where I have put the Y, which is to be obtained as 0. Now, Matlab is a user-friendly, very user-friendly package. I have a small, simple command, VD, eigenvector, and D meaning eigenvalues will be diagonal matrix. So, bracketed VD, you just write EIG H. H is your Hamiltonian matrix, which I have shown. I have taken 10 cross 10 out here. So we go to 11th slide now. V for V, please go to 11th slide. For V, I have columns, 10 columns of eigenvectors. You can see. Last two columns please look at. I have put them distinctly. And because from the command window of Matlab, I directly have copy pasted on the slide. So the numbers are not really very properly arranged. But one can see there are 10 columns. Please concentrate on last two columns. And now we go to the 12th slide, which gives me the eigenvalues as a diagonal matrix. This Matlab will do automatically. You do not have to think anything. You just write out your Hamiltonian matrix properly and give the proper command, and everything else will be taken care of by Matlab. And you can see that these diagonals are 10 eigenvalues, of which two of them, 0.8284 and 0.2195, they are positive to be retained. Baki, they are negative, rest of them to be thrown away. So we have here with 10 cross 10 matrix a slightly more improvement, as you can see. We have two eigenvalues. In fact, for hydrogen atom, we shall have in the first orbit S equals 0, that is, L equals 0, that is SH subshell 2 electrons. In the second orbit, 8 electrons, of which there would be S equal, there would be 2 S electrons and 6 P electrons. So for 2 S electrons, we shall have L equals 0. So indeed, for L equals 0, I require two solutions. One solution, this 0.8284, of course, is energy will be in dimensionless term minus 0.8284. This is your ground state energy, and the first excited state energy is minus 0.2195. I think I am clear to everybody. I am clear to everybody. Hello.
Please respond in the chat box.
Okay, very good, very good, very good. Then we go to 13th slide. So I have written down 0.4144 multiplied by Ke square upon A0, which gives me roughly minus 14.50 electron volt. That is our ground state energy. And first excited state energy is coming out to be minus 3.52. There is slight error, as you know, because ground state energy is minus 13.6 electron volt, you have told me. And the first excited state energy is minus 13.6 divided by 4. I think all of you know. So there is slight error, of course, expected, because still we are stuck with very few grids. I said number of grids have to be increased to 1,000, 10,000. Then computer can easily do it. Only thing is, I will not be as, please go back to 12th slide, or sorry, not 12. Please go back to 10th slide. 10th slide, yes. Only thing is, I shall have to, if I take 10,000 grids, I cannot write a 10,000 cross 10,000 matrix, of course, though it is a sparse matrix, even then I cannot write it down just like that. It is humanly impossible. I shall have to devise some code to write down such a matrix, which I have refrained here from because I wanted to give you a flavor of the calculation. So we come to the 13th slide, please. 13th. 13th. Yes. So now that we have found two energies admissible and corresponding eigenvectors or last two columns which I had indicated. So you have your x as s, which is 1, 2, 3, 4, 5 up to 10 because you have taken 10 grids. And y and y1 are the entries in the last two columns. Y corresponds to eigenvalue minus 14.50 electron volt, and y1 corresponds to minus y1 actually here is the actual value, because actual eigenfunction is expressible in terms of an exponential function multiplied by an associated Lagrange polynomial. So I have written down actual function as y1 for 1, 2, 3, 4 just to compare. And then I have given this command for plot, very simple command. And then we get in 14th. Please look at the graph on the right hand side. Please look at the graph on the right hand side. The one with crosses, stars, are our experimental graph, and one with these circles are our theoretical graph involving Lagrange, associated Lagrange and all that. So there is slight difference. I said the difference, we have plotted in fact along x-axis value of r upon a0, and along y-axis experimental value and theoretical value of what you call the radial solution r10. In fact, on the left hand panel, you can see actual plot of 1s, 2s, smooth, seamless plot, and 2p orbitals. 2p I have not ventured into because for 2p orbital I will have to take L equal 1. I think all of you appreciate this. So, you know, in all, I find that the calculation gives me sensible results, though inaccurate, slightly inaccurate, but sensible results. I think students also must be appreciating this. Now, up to this, I believe is clear to everybody. Is it? Is it?
Is this problem clear to everyone? Yes.
Okay.
Yes,
Okay. Now I have gone to screened Coulomb potential. Screening occurs due to the fact that if I have more than one electron, although then if one has more than one electron in Schrodinger equation, in TISC itself, electron-electron interaction must be introduced. We haven't done that. So suppose we have more than one electron. In our example, I have taken 4 electrons, of which 3 are dormant. They are only active to the extent they are screening or acting like an umbrella for the or shield for the interaction between one single electron and nucleus. So 4 electrons are there in the Z equal 4. You can see that 3 electrons are acting like shield, acting like umbrella, for interaction between fourth and the nucleus. And interaction potential then assumes the form, actually with detailed calculation one can see. Calculation of course leans very heavily on what you have done in the case of hydrogen atom, with single electron only, hydrogen atom being single electron system. So -2 plus 0.8 s for L equal 0. I'm sticking to L equal 0. Exponential minus 0.01 times s. That means I have assumed very weak screening. If I would have taken this term not 0.01, rather let's say 10, then it would have been a strong screening. But strong screening, if you are attempting to solve, that means you must have many more electrons which would provide a strong screening, and then electron inclusion of electron interaction in the Hamiltonian will be inevitable, and our whole calculation will become far too complicated. So therefore, not even moderate screening would have entailed writing a term of order 1 rather than 0.01. I have assumed very weak screening. So this is our potential. And rest of the things are almost same as hydrogen atom. Please go to the 6th slide. 16th slide, sorry. 16th, yes. Okay, so rest of the things are same. I have written down Hamiltonian matrix, and now I have how many terms? I had in fact made 20 grids. So a little improvement. Try to make a little improvement with S0, 0 and S21 also 0. So we have 20 grids, and I am giving same command, that bracketed VD is EIG of Hamiltonian matrix, and in the 17th slide it throws me back again only 2 positive eigenvalues. As you can see, negative eigenvalues are not written. Why clutter the space unnecessarily? And corresponding eigenvectors are y and y1. So with x as 0.1, 0.2 up to 2, and y and y1, these eigenvectors, I have plotted the graph of x, y and x, y1. So x is labeling r upon value of r upon a0, and y is labeling experimental eigenfunctions as function of r upon a0. We go to the 18th slide. We find the 2 eigenfunctions, like one which corresponds to the cross one for higher eigenvector, and this one to the lower one. So this is how this calculation, of course, is, I would regard as more of an exercise, because I have taken in the screened Coulomb potential. Please go back to 15th slide. 15th slide. In the screened Coulomb potential, I have assumed Z equal 4. With Z equal 4 meaning 3 electrons providing umbrella, a shield. well, then it necessitates introduction of electron-electron interaction into the Hamiltonian matrix. So that makes the problem beyond BSc level. Uh, Probably at higher level or at research level, one can uh, do attempt such problem. Uh, so I believe I've been able to give a flavor of how to solve a time-independent Schrodinger equation with Coulomb potential and with screened Coulomb potential using uh, Scilab, any other user-friendly package of Matlab and so on. So thank you very much. I think I have taken extra time. Is that so, Dr. Yogesh?
No, sir, not at all. You're on time always.
Okay. So any question? Like,
Participant, if there is any question, please write it in the chat box. Kindly post your queries. Yes, sir, there is one query. Let me read. For the last plot, can you show the ideal graph?
can you show for the last plot? Can you show
The ideal graph.
ideal graph?
Yeah.
Oh, yeah, I said there is there would be ideal graph indeed, but that would require inclusion of electron-electron interaction in the Hamiltonian matrix. Because I have taken Z equal 4 electrons. So how do you account? I mean, you have 4 protons in the nucleus correspondingly, isn't it? चलो आप इसको कैसे? How do you account for? You have to account for the electron-electron interaction, isn't it? So that makes Hamiltonian complicated. So at this level, it is not possible to show ideal graph.
Okay, sir. She got her answer, I think. Next question is from Akshita Goyal. Is it possible to determine energy shift due to the presence of field by numerical analysis?
Energy shift due to?
Energy shift due to the presence of fields by numerical analysis.
I mean, presence of what? I couldn't get it. Presence of?
Fields.
Fields.
Yeah.
Which field?
I don't know. Akshita, which field you are talking about? Akshita, magnetic field, sir.
Oh yes, magnetic field. Then with magnetic field, right? One would get what you call a Pauli type equation. Actually, magnetic field will make me replace momentum P by P minus E A. A is vector potential, E the electronic charge. So this change in momentum factor going to P minus E times A being vector potential of the magnetic field, will definitely alter the shape of the equation, which is called Pauli equation. There will be a magnetic field dependent term called Zeeman term, and there would be energy shift due to this term. Pauli equation is the basic one, and there would be involvement of Zeeman term. Zeeman splitting, if they have heard of. So there would definitely be energy shift. But again, that is an altogether very long story. One small point one needs to remember, that in presence of magnetic field, momentum P will get replaced by P minus E times A. A is vector potential of the magnetic field. How magnetic field and B and A related? B is curl of A. I think from electromagnetic theory everybody knows. B is magnetic field is curl of A. Is the student who is asking this question, is it clear to her?
Akshita, is it clear? Yes, sir.
Okay.
So, is there any other question? So there is no more question, sir.
Okay, fine. That's all right.
Thank you so much. I think it is
Yeah.
really a great lecture by you. Preeta ma'am is here.
Yes, of course, I'm here.
Great
I've been
lecture.
patiently waiting and listening. I just mentioned on the physicist group that all the teachers who are teaching quantum mechanics Scilab should be actually tuned into this lecture right now. And if not right now, then later they must connect and see how nicely sir has explained the quantum mechanics Scilab
Yes.
today, how the solutions should be done, and so on. And it's amazing,
No,
sir.
I'm
Actually,
honored. I'm honored.
you see, sir,
Thank you
actually,
very
you
much.
should,
I'm honored.
even for younger colleagues, you should. I think you should hold these type of classes which are required, because for Matlab and Scilab, this kind of understanding is not uniform everywhere. It was a wonderful lecture, and I think students
Thank
did
you, madam.
understand
Thank you very
something,
much.
because nowadays physics has computers everywhere. You need to program in almost all the laboratories of all the universities in India.
Yeah,
So either
definitely.
Matlab or Scilab or Python or something like that. And therefore,
Right.
it is necessary that we understand how we should go about it. Thank you so much, sir. I'm really
Thank
grateful
you.
that
Right.
you agreed
Thank you.
agreed to give a lecture to us. And
Right.
And
it's great
Thank
student,
you.
to
I
hear. And I again request you, sir, if you make further recordings for your own students, we would like to connect. We would like to connect your videos to our channel so that the students can benefit from your lectures even when this particular webinar series is over.
Yeah, definitely, definitely. I would. I'm in the process of making video of the barrier problem, potential well problem. Students find it very difficult to solve for the reflection and transmission coefficients, and show that in particular R plus T equal 1, which follows from energy conservation. So
Very true, sir.
I would in shortly I would make such videos, and then I will share. Right.
Yes,
yes,
I asked you this purposely because the students are listening, so they know that they can follow this channel even after this webinar series is over. Because I would try to upload more videos of physics which can help them on this channel later on also.
Yeah,
Thank you so much, sir.
definitely, definitely. Thank you.
Thank you so
Thank
much.
you.
thank you very much, sir.
Thank you.
Yogesh, Dr.
Thank you.
Yogesh.
Yes,
Acha,
sir.
ma'am, for a moment, can you switch off the mic? Yogesh had, can you switch off the mic for a moment?
Your mic.
From public, from students. I mean,
Sir,
students
1 minute.
not
Sir,
get.
1 minute. Sir, 1 minute. It cannot be done because it's going live. It's going live,
Oh, oh,
and
oh.
and it's also
Yes.
recorded. Therefore, sir, I shall speak to you on phone or something.
Exactly.
Yes,
This
yes.
is regarding Yogesh. This is regarding Yogesh. I tell you before.
Okay, sir, we discuss it on phone then. So,
Right,
Dr.
right.
Yogesh,
Okay,
please
ma'am. So I'm
stop
yes,
the
yes,
live YouTube and the local recording, please.
Right.
yes, ma'am.
Thank you.
Yes, ma'am.
Thank you.
I'm just